So we are going to do another partial differential equation solution by separation of variable today. And then we're going to, next week, just do some like fun special topics while you guys are working on your homework for the, over PDEs, which is just one problem now. It got updated, so if you checked before, it had the Kreisig problems on it. I took those down, and we're just doing the one at the end of this chapter 7. I'll give you guys the final exam. I can't decide what day I'll give it to you because I have to give you guys some time to finish the homework too. So I'll give you guys some time to finish the homework, and then we'll do the final, which will be a few days probably. So
take a few days to write, and then take us how long to finish?
Right. Yeah. Exactly. Well, it takes me a long time to write them so that it doesn't take you guys too many days to finish them. So yeah. So that's kind of the plan. Lecture 7.4 then, the 1D wave equation. So the one-dimensional wave equation is the linear PDE given in 732, where we have something similar to the diffusion equation or the heat equation, as it's sometimes called, that we did last time. But this time we have the significant difference is we have a second time derivative on the left-hand side. So instead of there being a first time derivative, it's still a one-dimensional equation with real constant c here. C squared is what we choose to call the constant there. It's just a convenient way of doing it to make it squared. You could just leave off the squared if you wanted to. This equation models such phenomena as strings vibrating, okay, fluids, sound, and light. So like pretty much anything that behaves like a wave can be described, at least in some instances, with this PDE. So you guys have probably seen this show up. If you took the vibrations class, the vibrations class certainly had this equation in it. Probably it was derived from first principles, taking a single element and looking at it in the string. And you probably also did that for a beam as well in the vibrations class. So it's pretty common. You may or may not have seen this in fluids, but it does show up in fluids as well. And in physics, you would see the light and the sound ones. Although typically when they teach you undergraduate physics that engineers take, usually they don't get into the PDE part of it too far. This equation is subject to initial and boundary conditions as usual and can be extended to multiple spatial dimensions. So we're just doing 1D, but you can do 2D and 3D. For 2D and 3D examples in rectangular and polar coordinates, you can see a couple sections of Kreisig, and also the Haberman text has it as well. They're pretty nice treatments. But I thought we would just go ahead and do our treatment in just the same way that we did the last one, just to see the parallel way that we can solve these equations. So consider, so here's the example, vibrating string PDE solution by separation of variables. Consider the 1D wave equation PDE, given here, so this is the same one as above. With real constant c and Dirichlet boundary conditions on interval from 0 to L. This is oddly spaced, but they're both 0 at the ends. So if it's a string that we're modeling, then we're holding the ends of the string stationary at the same position. And with initial conditions, we need 2 initial conditions because of the second time derivative. Okay, so we need the initial condition f of x, which is the distribution that the string starts in. So how is it initially positioned, and then the time derivative of that is what's the initial velocity of the string as a function of space, g of x, where f and g are some piecewise continuous function on 0 to L. For your question?
Not yet.
Okay. Good. So the first thing we do, just as before, we assume a product solution. So there's a time variable and a space variable. We say that our solution hopefully is going to be able to be written as a product of a time solution and a spatial solution. And then we try to separate the partial differential equation, substituting into our product solution into our PDE. We see that it is in fact separable in a very similar way to how we had it separable before. Once again, we group group C with T, which was arbitrary but conventional. Since these two sides depend on different independent variables, this is T double prime. They must equal the same constant we call negative lambda. So we have two ODEs given here, and this is T double prime, T double prime. And so we've got two similar looking ODEs to solve. And we'll solve them first for matching the boundary condition, boundary value problem. The latter of these equations with the boundary conditions here from above, the Dirichlet boundary conditions, is precisely the same Sturm-Liouville boundary value problem from example 7.2-1, which had eigenfunctions given here and eigenvalues given here. So that was, it's a boundary value problem that shows up in a lot of problems, okay? Wave equation and the heat equation. It shows up if you do a membrane as well, okay? Membrane equation is the wave equation in two spatial dimensions. And I almost did that one for you guys, but it's just a longer problem. It's just you have to do two boundary value problems for a two-dimensional spatial domain. So it gets a little bit messy, but essentially they come down to like the same boundary value problems over and over again, which is nice. Yeah. Solve the time variable ODE. The time variable ODE is homogeneous and with lambda restricted by the reals to the reals by the boundary value problem. It has the familiar general solution that the time solution is a sinusoid, right? With some phase and amplitude. So K1 and K2 determine what that phase and amplitude are going to be. However, the boundary value problem restricts values of lambda to lambda n, so we can say that the time solution for a given n is given by this expression where we plugged our lambda n in there for lambda. Okay, construct the product solution. So we have our solution, our eigenfunctions for x. We have our time solution. Now, notice it's kind of nice because when we solved the time one, we didn't have to consider the complex lambda situation because we knew that we had real eigenvalues. Those are the only ones that we have in our boundary value problem solution. So we don't need to go into like, okay, if it's, if we have complex roots, it's this. If we have, but they're always going to have exactly, these are going to always be positive. So that was nice. Real and positive. So we get this product solution where we take the time solution and we multiply it by the space solution. So that's just the two multiplied together. They both have sinusoidal aspects to them. One of them is just a sine. That's the spatial one. The time one has a cosine and a sine. That's why we get the two terms. This is a family of solutions that each satisfy only only exotically specific initial conditions, right? Just one of these terms it would only be the case if you happen to have a sinusoidal initial condition, and that would work. Otherwise, it wouldn't satisfy them. Recall that superposition tells us that any linear combination of product solutions is also a solution, okay? Therefore, this infinite sum of linear combinations of these solutions is a solution, okay? If an and bn are properly selected to satisfy the initial conditions, equation 744 will be the solution to the entire problem. Okay. Substituting t equals 0 into our potential solution gives these two results. So I just plug in t equals 0. The cosine term becomes 1. The sine term becomes 0. That has t in it. And then we're left with these two possibilities. So this is when you plug it directly into 744, with time equals 0, you get this. You take the time derivative of this, first time derivative of this, and you plug time equals 0 into it, you get this. Okay, just an easy differentiation. Okay, so let's extend f and g to be periodic and odd over x, just like we did last time. We said, okay, we have a periodic extension of the whatever that function is from 0 to L. We call the extensions f star and g star. From equation 745, so these two that we just derived here, the initial conditions are satisfied if we have f star being equal to this series, and if we have g star being equal to this series. Okay? So that's what we need for our initial conditions to be met. We identify these as two odd Fourier syntheses. They only include sine terms, so they're odd Fourier syntheses. The corresponding Fourier analyses are, first one's straightforward. It's just that an is going to be just the an formula from the Fourier sine series. You just have to integrate your f star to get each of these an values. The bn one takes a little bit more interpretation because this entire term has to be equal to the Fourier component that's being computed here. So the analysis is for bn times cn pi over L. If you forget that factor, obviously you're going to be off. So it's an important factor to include. So the complete solution is 744 with components given by 747. Notice this satisfies the PDE, the boundary conditions, and the initial conditions. Discussion. It can be shown that this series solution is equivalent to two traveling waves that are interfering. So there's an extensive discussion of this in both of those texts. This is convenient because computing the series solution exactly requires an infinite summation, right? Anytime we have a series solution, we always have that problem where, well, actually computing an infinite series takes time. We show in the following that the approximation by partial summation is still quite good, but what's nice is two traveling waves. It takes some derivations, a little bit long. But you can show that these series sum to transcendental functions, sines and cosines that are shifted in time and space. So they're traveling, meaning that they move in space. So it's pretty cool. So we can actually come back to an analytic non-summation solution in this case, but it doesn't happen in most cases. So it's sort of like we luck into finding this solution. But it is in general nice to use. I decided to just say, we're not going to go that route. We're just going to do our summations and approximate it, doing partial sums. So choosing specific initial conditions. If we want to plot solutions, we need to specify initial conditions over 0 to L. let's model a string being suddenly struck from rest as being flat to start, f equals 0, and then G having a Dirac delta impulse at delta times L, okay? Where delta then is a fraction of L, and it tells you where you're going to strike the string on the length from 0 to L. So we're going to say, okay, if you put in this very high spike, right, of speed, right at a certain location on the string, what happens to the string? Like what happens to the position of the string over time? So that's what our goal here is for the solution. The odd periodic extension is an odd pulse train. The integrals of 747 give an is going to be 0 because you're integrating over 0, so it's nice. The bn's are non-zero, and there's this really nice way to evaluate the integral. The integral is using the sifting property of the Dirac delta function, just the function that you're multiplying the Dirac delta function by, evaluated at the value of, I guess this would be d chi. I missed the chi here, d chi. So you're at the value of chi, where delta is undefined technically, or where it has its impulse value. So that happens at delta L. So we plug delta L in for chi, and that gives us our integral. And the L's cancel, so you have n pi delta inside the sign, and it's a nice simple expression for Bn. Pretty sweet. We can now write the solution, and I mean it is good. It's a good way to model a string that gets suddenly struck to give it some impulse initial velocity at that point that it's struck. It's a reasonable thing. It's also something that I chose because I knew it would be easy to integrate over. So when you choose your value, or when you choose what your initial conditions are, if you choose it to be something that's hard to integrate over, it's going to be a lot more work to find these final solutions, right? So that's something to keep in mind when you're modeling something. You could have picked like a Lorentzian or some other like sort of shape, but don't have to make it harder on yourself than it has to be. I think getting down into like what's the best model is an interesting question, but we're not going to explore that here. So here's our solution for that initial condition. So plot it up in Python. The first thing I wanted to do is plot the solution in space at different snapshots in time. So it's not quite time equals 0. It's very early, right after it's struck. We have this like sort of square wave develop in the string, and that square wave starts to travel rightward. Okay, so here's the next one, is the next blue one here. It turns into black as it gets here, and so it has a sort of a smaller width as it comes to the end, and then it has a larger width as it travels across, but it doesn't increase really. It just stays fixed width until it hits the other side, and then it actually flips, and it travels back this way downward. So it has this like square wave look to it until it hits over here, and then it flips back up this way, and we get the last value of time, like 0.184 is this one here. So we see this just going to keep looping around. So that's our sudden striking of a string. The wave travels around like that. So I chose the what did I choose? The delta value to be 0.1. It's interesting to play with this parameter. The closer you do this to the endpoint, the smaller the width of that wave is. Okay? If you do it right in the middle, it grows outward and then it comes back inward. It flips inward. So it goes out and then back in, like symmetrically. And it ends up looking, when we look at the color plot, it looks like an Argyle sweater. It's kind of interesting how that works. But what I did was I used the 0.1 delta, and you see this is where we strike the string here, and it creates this wave of that width, and then it starts to move that wave across, right, until it hits the other side. And what you can think of is that you still have an up part of the wave that's happening, and you have like a canceling down part that's canceling this part out until you get all the way to here, at which point it sort of is fully crossed over. Now it starts to grow on the other side. And we see it move back the other way, negative, and then it flips again and goes back the other way. So it'll just go back and forth. If you start this in the middle, actually, probably wouldn't be very hard for me to do that. Let's see. I'll move this over. Let's start it in the middle and do that calculation. Here, so I'll do delta 0.5. What you see is the wave grows outward, and then once it hits the outer edge, it flips the whole thing, and then it comes back inward, and it shrinks to a point. So when you look at this, it looks like an Argyle sweater. It's weird, but what's happening is that it grows out and then it shrinks back in, and then it crosses over itself and it flips over, goes back out, comes back in, flips over. Yeah, so that was kind of a cool one. Kind of liked that one. And notice these are we've got this approximations. We can get better and better with them if we add more and more terms. I summed, for these plots, I summed 150 terms. Could have gone to more and gotten a better plot. What I was actually running into was the only issue that I was having when I went to more and more. It didn't take very long to compute it in Python, but what took a while was getting the exported figure to come into LaTeX. It would exceed the memory and stuff, so he didn't like pulling it in because there's just so many points to find. He didn't like that. So there are different things you could do to mitigate that. I decided not to. I was like, I could do smoothing on it, and I was like, no, that's not what I want to do. But we could notice that. I mean, you can already see you could define this as a wave, a square wave that is moving in two different directions. It's traveling two different directions and keeps overlapping, like interfering and de-interfering. So you can kind of see this emerge where you've got two waves. One's positive, the other's negative, and they keep interfering with each other, canceling each other, and then they're just moving in different directions. So that's the two traveling waves solution that you can see kind of emerges here, and you can show it analytically too if you go through the trouble. Most of the derivations, I think, assume zero initial velocity for the traveling wave solution, but you so in our case it wouldn't apply, but I think the solution is valid in both cases. In any case, it's pretty fun stuff. So now we've seen the diffusion equation, which models like heat flow especially, but the diffusion of so many different things. Diffusion is a very common process in the world. And then we have also seen the wave equation. These are the two most important PDEs. The wave equation, getting solved in multiple dimensions, is important too, but it builds off the same thing. So all you have to do for the two-dimensional wave equation for simple geometry is your boundary value problem. You separate variables once. You see that you have an ODE in time and a PDE in two spatial dimensions. Then you separate that PDE in the two spatial dimensions into X and Y. You can also do it in polar coordinates as well. And you end up with 3 independent solutions. It is separable, and you can do the boundary value problems. And so, with reasonable boundary values given boundary conditions. So it's pretty. You guys have seen kind of like the big two now, and there are other methods. You can use Laplace to solve PDEs as well. There's this Dalembert's solution method that works for the wave equation, I believe it is. It's an alternative solution not using separation of variables. And there are some other, there are some 3D cases you can look at that are kind of cool. So like looking at the heat equation in 3D, for instance, is pretty interesting. So these equations, and working through them in separation of variables like you've done, working boundary value problems like you've done, this gives you a good taste of what PDE solution is like. There are other techniques. They are pretty specific to certain problems. So part of what you should really focus on taking away from this is understanding how to classify which type of PDE you're working with so that you can consider the right solution techniques, know if there is a solution technique that will work for you, know when there's probably not going to be a solution technique. For instance, when it's a nonlinear PDE, for the most part we don't have solutions to those. So this is, I love how many different fields this pops up in PDEs. So it's important to understand kind of how to build solutions to it, how we used Fourier analysis to construct superpositions of our boundary value problem solutions, the eigenfunction solutions, to meet our initial conditions. That's another sort of key aspect of solving these problems. So so I think that taking those things away is going to be valuable. And when you get to a nonlinear PDE, or one that's in several dimensions but doesn't have a solution for the geometry that you're working with or the boundary conditions that you're working with, knowing how to approach it numerically is an important thing to do too. So I encourage you to study further on that. Dr. Einstein is offering the 503, MME 503 course in the spring, and that course has a treatment of this numerically. So this is the sort of part where it jumps off to numerical analysis when you go beyond this. Okay. All right. Any questions on PDE solutions, boundary value problem solutions? We're going to now move on to some fun special topics in the last week while you guys work on homework and the exam. So, okay.